Welcome to the class. In this video, we'll learn about the adjoint of a matrix, singular and non-singular matrix, invertible matrix, and finding inverse of an invertible matrix using adjoint. So let's start. Adjoint of a matrix. The adjoint of a square matrix A is defined as the transpose of the matrix formed by the cofactor of its elements. For example, let A be a 3 by 3 determinant. Therefore, adjoint of a matrix A will be given as transpose of its cofactors A11, A12, A13. These are the cofactors corresponding to the elements A11, A12, etc. So adjoint A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Once again, A11, A12, these are the cofactors of the element A11, A12, A13, etc. Now important theorem 1. If A be any given square matrix of order n, then A into adjoint of A is equal to adjoint of A into A is equal to the identity matrix, where I is the identity matrix of the same order as A. Let us verify it. Here LH is equal to A into adjoint of A is A11, A12, A13, A21, A22, A23, A31, A32, A33 into adjoint of A A11, A12, A13, A21, A22, A23, A23. Now multiplying we'll get A11. This will be multiplied with this into A11, first element of the product determinant, plus A12 into this A12 plus A13 into A13, first element of the first row. Now second element of the first row will be equal to A11 into A21 plus A12 into A22, A12 into A22 plus A13 into A23, A13 into A23. The value of these C products will be 0, as we have learned in the previous video. You may refer to page number 124 and 125 of the NCERT textbook. Similarly, the element in the second row and the first column will be 0. The element in the second row and the second column will be determinant of A, and the last element will be 0. A31, that is the element in the third row and the first column, will be 0. This will be 0, and the last element will be again determinant of A. So this will be equal to determinant of A 0, 0, 0, determinant of A 0, 0, 0, determinant of A. As this is a matrix, so we can take out determinant of A common from whole of the matrix. We'll get 1, 0, 0, 0, 1, 0, 0, 0, 1. That is determinant of A into I. determinant of A into I. Now singular and non-singular matrix. If determinant value of a matrix is 0, then it is called singular matrix, and if determinant value of a matrix is not 0, then it is called non-singular matrix. Now we'll write two theorems without proof. First one, if A and B if A and B are two non-singular matrices of the same order, then AB and BA are the non-singular matrices of the same order. Next theorem is the determinant of the product of the matrices is equal to product of the respective determinants, that is determinant of AB is equal to determinant of A into determinant of B, if A and B are the determinants of the same order. Now one more important theorem, theorem number 4. A square matrix A is invertible if and only if A is non-singular. Let A be a square matrix of order n, and let there exist another matrix B of the same order such that AB is equal to BE is equal to I. This implies AB is equal to I. Taking determinant on both the sides, AB is equal to determinant of I. This will be 1. As per the theorem number 3, this will be determinant A into determinant B. Now the product of two determinants is equal to 1. It means that neither of them is 0. It means that determinant A is also not equal to 0. This proves the determinant A is non-singular. Now let A into adjoint A is equal to adjoint A into A is equal to determinant of A into I. Transposing, we'll get A into is equal to 1 by determinant A into adjoint A into A is equal to I. This implies A into B is equal to B into A is equal to I. It means that B is the inverse of A. So A inverse will be defined as this, or you can take this. A inverse is equal to 1 by determinant A into adjoint A. That's all for now. In our next video, we will solve problems based on adjoint and inverses of 2 by 2 and 3 by 3 matrices. Thank you.